Welcome to lesson number 3 on mole ratios. Our objectives for this lesson: calculate mole ratios for chemical reactions. When we think of chemical reactions, we should think of a recipe. And so in a simple recipe here, we have some cake mix. We require 2 eggs and 1 cup of water. These are our ingredients, or in chemistry we call the reactants, because we're reacting them together to produce our product, in this case, 1 cake. Just like a regular recipe in chemical reactions, if we want to, let's say, make 2 cakes or a half a cake, or we don't have all these ingredients, or we have more ingredients we want to use up, we can alter this recipe. So we can triple it, we can double it, we can half it. The amount of ingredients can change and will alter the amount of products that we make. For example, if I wanted to use 2 boxes of mix, and I had an unlimited supply of eggs and water, then if I have 2 boxes of mix, I can make 2 cakes, because the original ratio is 1 of these makes 1 of these. So if I double my mix, I double my product. Looking at the eggs, original ratio is 2 eggs makes 1 cake if I have an unlimited supply of water and mix. So now if I use 6 eggs, that's 3 times the amount of eggs. I'm going to make 3 times the amount of my product, which would be 3 cakes. And notice the ratio hasn't changed. If you divide 6 and 3 by 3, you get a 2-to-1 ratio, just like the original ratio of 2 eggs to 1 cake. So in a chemical reaction, it's the same thing. So the big numbers out front, instead of those things being like the amount of eggs or a cup of water, they represent how many moles of that substance are required. So for the reactant side, our ingredients, we need 4 moles of aluminum and 3 moles of oxygen, and that's going to yield or produce 2 moles of aluminum oxide. So these coefficients tell us how many moles of the substance are needed in this reaction. So how do we calculate mole ratios if we want to change that recipe? If, for example, I don't want to make 2 moles of my product, I only want 1 mole. Or what happens if I only have 1.5 moles of aluminum? We can set up a mole ratio. So the first thing you do is you set up a ratio of moles, a proportion of substances in the balance equation to the actual values they give you, and then we're going to solve for the unknown. And it's important at the end to make sure that the new ratios are the same as the original ratios. If you remember from class, our POGL, the ratios cannot change. So let's see an example. How many moles of oxygen are consumed, meaning used up, when 0.6 moles of hydrogen burn to produce water? So here's our reaction. And the original chemical recipe right now calls for 2 moles of H2, 1 mole of O2, producing 2 moles of water. But we want to change that. We want to use only 0.6 moles of hydrogen here instead of 2 moles. So the first thing we do is we set up our proportion. So we put the 0.6 moles of hydrogen under the hydrogen here. And then how many moles of oxygen? That's going to be my X. And now we have a proportion set up. What we can do is we can rewrite it to make it more clear. So 2 to 1, and then 0.6 to X. And then simply just solve for X using cross multiplication. So 2 times X is 2X, 0.6 times 1 is 0.6. When you divide 0.6 by 2, you get an answer of 0.3 moles of O2. Now I said to go back and see, are the ratios the same? So let's look at the original ratios. We have hydrogen to oxygen, so it's a 2-to-1 ratio. So just because we're changing the recipe, the ratios must be the same. So now we have 0.6 to 0.3, and you divide both those by 0.3, you get a 2-to-1 ratio. And we know that we have a correct answer. Let's see another example. How many moles of nitrogen gas, N2, would be needed to produce 10 moles of ammonia, NH3, in the following reaction? So right now, the original recipe calls for 1 N2, 1 mole of H2, producing 2 moles of NH3. And we want to produce 10 moles of NH3. So we set up our proportion again. So the 10 moles of NH3 goes here. How many moles of N2 do we need? That's our X. If you want, we could rewrite this. And then here's our proportion, and we're going to cross multiply. So 1 times 10 is 10, 2 times x is 2x. When we divide 10 by 2, we get 5 moles of N2. So what does that mean? It means if we want to make 10 moles of NH3, we need 5 moles of N2. Let's check our proportions. So the original recipe called for 1 mole of N2 to 2 moles of NH3. So it's a 1 to 2 ratio. And looking at it now, we have 5 to 10, which is, when we reduce that, a 1 to 2 ratio. Let's see one more example. If 12 moles of C3H8 react completely, how many moles of H2O are formed in the reaction below? So we want 12 moles of C3H8. So right now the recipe calls for 1 of these to make 4 moles of water. We want to change this to 12. So we can put this over 12, and of course we're trying to find out how much water we would make, so that would be our x. When we cross multiply, 1 times x is x. 4 times 12 gives us 48 moles of water. Again, check our ratios. So we have a 1 to 4 ratio, and so this is 12 and this is 48. Divide both by 12 and we get a 1 to 4 ratio. Let's check your understanding. Can you calculate mole ratios for chemical reactions? At this point, you should be able to calculate mole ratios for chemical reactions.